Okay, let me introduce Professor Jessica Sidman from Mount Holyoke College, who was a co-organizer of the just previous Discrete Math Day at Mount Holyoke, and she's very active in combinatorial algebraic geometry, computational computative algebra, rigidity theory, spanning the subjects of matroids, geometry, and with applications to things like computer vision. So we welcome Professor Sidman, and here we go.
Okay, so I want to begin by thanking the organizers for first the opportunity to speak to you all today, and second for their very quick reimagining and re-envisioning this, this conference to put it online and bring us together virtually. So thank you all. I'm going to be talking about a project that I started about 1.5 years ago with Will Travis, who's at the Naval Academy, and Ashley Wheeler, who's currently at Mount Holyoke, where I am. And what we've been thinking about are geometric equations for matroid varieties. So you don't have to know what any of those words mean. I'm going to try to sort of define them as the talk goes on. I want to try to start with something that we're all familiar with, which is a matrix. And actually, now that we're all working from home, my 9-year-old came into my office the other day and saw my notes and said, "Oh, a matrix. I know what a matrix is." And I said, "Really? Like, tell me, what is a matrix?" And he said, "A matrix is an array of numbers." And I said, "Pretty good. Okay, apparently you know what a matrix is." So we all know what a matrix is too. And the question I want us to think about first is, what is the combinatorics of a matrix? What might we mean by that? And so I'll tell you what I mean by that. And what I mean is I want to think about the columns of the matrix, and this matrix has 7 columns. And I want to think about the sets of columns of my matrix that are linearly independent. And that's what I want to call the combinatorics of a matrix. So in particular, let's let E be the set here, 1 through 7. And then I'm going to define a set script I to be the subsets of E that index linearly independent sets. So for example, if I call my columns of my matrix AI, then I'm going to look at the subsets that index these so that that set would be linearly independent, okay? And of course, if you've seen this before, what I'm really doing is I'm defining a matroid, okay? So what's a matroid? If I have any matrix, I can associate to it a matroid, and that's a finite set, and the set of column labels for the matrix, and a set of subsets of the columns that index the linearly independent sets of columns. So this is a matroid. And a matroid is really, it's an abstract object. So if I give you any non-empty finite set E, I can declare certain subsets to be independent as long as they satisfy basically a couple of rules, okay? And the rules are derived from the properties that linearly independent sets of vectors satisfy. So what are those properties? Okay, so let's think about this. If I have a linearly independent set of vectors, then any subset of that set should also be linearly independent. So that's one of the 2 rules that independent sets of a matroid have to satisfy. The other one is that if I have 2 subsets of vectors in the same vector space, and one is bigger than the other, then I can take an element from the bigger set, throw it in, there's at least one element from the bigger set that I can throw into the smaller set to get another linearly independent set of vectors. So those are really the axioms that independent sets of a matroid have to satisfy. And if I have those axioms, then I can start to define all the other things that go on in vector spaces. Like once I have my independent sets, I can look at the ones that are maximal. and those are bases of my matroid. I can look at the subsets of E that I did not declare to be independent, and those are the dependent sets. I can look at the minimal dependent sets, and those are circuits, etc. Okay, so matroids are these abstract gadgets that sort of axiomatize independence. And whenever you have a reasonable notion of independence, you'll have a matroid, right? So for example, they were really defined to bring together the notions of independence in vector spaces and in graph theory. And in graph theory, your set E is going to be the set of edges of your graph, and you're going to declare any subset of E to be independent if it contains no cycles. Okay, so when I first learned about matroids, they seemed like very abstract gadgets to me, and I couldn't quite figure out what I was supposed to do with them. And it wasn't until I started working in rigidity theory that I really came to see the light in terms of matroids and see how useful they are and kind of unifying, giving a unifying structure for thinking about independence. Okay, so that's what I mean by the combinatorics of a matroid. And now the question that's really going to be the focus of my talk is the following, which is, well, how can we describe the following set? So how can we describe the set of all matrices that give rise to the same matroid as the one I just started with? So in other words, I'll be looking at matroids of this matrices of the same size, so 3x7 matrices, and I want them to have the property that if I associate a matroid to the matrix B in the same way that I just did, right? So I'll look at the column labels of B, and I'll try to find out, I'll declare a set to be independent if the set of columns that it label, indices, is linearly independent. And I'll want that to be the same matroid that I started with. Okay, so that's really what I'm talking about, is how can I describe this set? And as Seth mentioned, introducing me, so I'm sort of trained as an algebraic geometer. So when I say, how can I describe a set? What I'm really thinking of is the question, well, how can I describe it with polynomials? In other words, I'd love to have my set. Okay, so that's really what I'm going for now. So let's see. Are there any polynomial equations that the entries of a matrix B would have to satisfy if the matroid associated to the matrix is the same as the matroid that I started with? All right, well, so there's some that are relatively easy to derive. So let's look at this matrix for a minute and notice that if I look at columns 1, 2, and 7, if I just took the 3x3 submatrix on the columns 1, 2, and 7, I get a bottom row of all zeros. So certainly those vectors 1, 2, and 7 are not independent, those columns. So I'm going to say that the set 1, 2, 7 is clearly not in my set of independent sets, okay? Well, what that means, because we all know linear algebra, is that if I look at the 3 corresponding columns, so A1, A2, A7, and take their determinant, I'll get 0, okay? So what is this thing? I can think of this determinant as a degree 3 polynomial in 9, so in 9 entries of the matrix A. And any matrix that has the same matroid as A is going to have that 1, 2, 7 is not a basis. So 1, 2, 7 is a dependent, so this should be not in I. 1, 2, 7 is not in I, right? So the 3 columns, 1, 2, and 7 will have to have determinant 0. And I'm going to write shorthand for this determinant. Instead of writing what I wrote, I'm going to write a bracket where I'm just going to put the column labels in a bracket. And for this talk, I want you to think of that bracket as literally being the number that is the determinant of columns 1, 2, and 7. Okay, so what other relationships, polynomial relationships, do I have to satisfy? So in addition to columns 1, 2, and 7 being dependent, I can see if I look at columns 3, 4, and 7, then the middle row is all zeros. So I also will see that, that 3, 4, 7, that determinant has to be 0. And if you look again at 5, 6, and 7, you'll see the second and third columns are exactly the same. So then that tells me that the bracket 5, 6, 7 also has to be 0, okay? So those are all that, now I have 3 degree 3 polynomials, each that would be using 9 entries of a matrix that would have to be 0 if that matrix has the same matroid that I started with. But there are some other polynomials that also have to vanish. And there's a polynomial that I want to call, I'm going to give it a name because we're going to use it more than, we're going to see it more than once. And it's this polynomial. So it's the bracket 1, 3, 4 times 2, 5, 6 minus 2, 3, 4, 1, 5, 6. So I claim this equation has to be 0 for any 3 by 7 matrix that has the same matroid as the one I started with. And why? It's a little mysterious right now. So this one, at least right now, at this point in the talk, should be a little mysterious to you. You might say, well, what can I do to understand this polynomial better? Should I write it out? So I've sort of hidden what it is, right? But by writing it in terms of brackets, let's remember that this polynomial really has degree 6 in 18 entries of my matrix, in 18 entries. So actually, writing it out in all of its full glory with every single entry of the matrix in it probably isn't going to make it more easily understandable by a human, okay? It's kind of big and hairy. But what I want to do over the course of the talk is find a way of rewriting this polynomial using geometry and combinatorics, so that we really can see where this is coming from and what relationships it's encoding. Okay, but I'm not going to write my polynomials out in individual variables. I'm going to stick with brackets. And actually, sticking with brackets means I'm really working in a slightly different setting. So I want to change gears a little bit right now. And instead of asking questions about matrices, I want to actually ask questions about subspaces instead. So let's take a look now at our true setting. So where am I really living? So our setting for the rest of the talk. So I want to let X be a linear subspace of C to the n, where the dimension of X is equal to K. And I'm going to associate matroids to subspaces instead of associating matroids to matrices. So a subspace, a k-dimensional subspace of C to the n is really the same thing as a point. Oops. It's the same thing as a point in the Grassmannian GNK. So this is the Grassmannian of k-planes in C to the n. So this is it's a manifold, it's a variety whose points correspond to subspaces, okay? Well, I do want to get matrices involved again. So if I have a k-dimensional subspace of C to the n, and I pick a basis for it, I'll get k length n vectors. And I'm going to write those as rows of a matrix. So I'm going to write AX as, this is a k by n matrix, so k by n matrix, whose rows are a basis for X. So it's row space is my subspace X. And then I can say, well, I'm going to define the matroid associated to this subspace to be the matroid that I would associate to that matrix. Okay, so I look at the columns of the matrix and I declare a set of the column indices to be independent if the set of columns that they index is linearly independent. And you might say, hold the phone for a minute. Bases aren't unique, so I'm not going to get a well-defined matrix AX for every subspace. And you're right, that's fine. But if I take a change of basis, let's think about what change of basis does to a matrix. So it's not gonna vary the row space at all, right? Because it's just a change of basis. The column space will change if I take a different basis for the row space. But one thing is preserved, and this is really important. The sets of columns that are linearly independent, those stay invariant under a change of basis for the row space. So even though if I take a k-dimensional subspace and I take a k by n matrix whose rows are a basis for that space, the matrix isn't unique. The sets of linearly independent columns are. So I get a well-defined matroid, even if not a well-defined matrix. Okay, so what else should we know? Just a little bit more about Grassmannian stuff. So where does this weird space whose points index k-dimensional subspaces of C to the n, where does it live? Well, I claim that the Grassmannian G and K sits inside of a projective space, P to the n choose K minus 1. So where does that come from? Well, once I get one of these K by n matrices, I can look at the n choose K length vector of K by K minors of this matrix AX. These K by K minors are exactly the brackets that I was talking about earlier. And if you're used to Grassmannians, you'll realize that these brackets are exactly the Plücker coordinates. So these are the Plücker coordinates of my subspace. So again, this length n choose K vector is not well defined because I could have picked a different matrix if I picked a different basis for my subspace, but any change of basis, what does that do to this vector of brackets? It just changes all the brackets by the same determinant of that change of basis matrix. So up to a non-zero scalar, this vector is well defined, and that's why I'm really living in projective space, okay? All right, so now, where are we? Suppose I pick a point in my Grassmannian. So I have a k-dimensional subspace of C to the n. And I'm going to look at the following set, call it gamma x. And this is the set of all other points in the Grassmannian that give rise to this same matroid that X does. And if you think about it, for every point in the Grassmannian, I get a matroid this way. So every point of the Grassmannian is in one of these sets, gamma X. These sets partition or stratify the Grassmannian. And I think it was in the 80s, so there's a beautiful paper of Gelfand, Goreski, McPherson, and Serganova, where, called the Matroid stratification of the Grassmannian, where they talk about the beautiful combinatorial and geometric relationships in this paper. It's really, really lovely. I'm not actually interested in these sets gamma x because I'm an algebraic geometer and I wanna think about how to describe these sets using polynomials. So actually, I'm interested in a slightly different set that I'll call Vx. And so Vx is what I'm going to define to be the Zariski closure of gamma x. So if you don't know what that means, it means the following. It's the Zariski closure is the smallest set containing gamma x that arises as the solution of a system of polynomial equations, okay? And this is the thing that I want us to call a Matroid variety. And it's the Matroid variety of x. And I want to try to describe it. I want to know how do I find this using polynomials? So the thing I'm really interested in is what I'll call Ix. And as a set, this is the set of all polynomials written in terms of these brackets or Plücker coordinates that vanish on all of the Matroid variety. So this set, if you know algebraic geometry, is an ideal. And what I really want to know is, what are the polynomials that generate all the other polynomials in this set? Okay, and in particular, which polynomials are in this ideal? So that's the question that I'm really turning to now. Which polynomials are in this ideal? Okay. Well, there are some that are kind of obvious. So let's think about those first. And I claim that if we look at this set that I'm going to call n sub x, these are the ones that are kind of trivially in there. And we've sort of seen some of them before. They're just brackets that correspond to non-bases. So I look at k element subsets of columns where those k columns are not a basis. So the k by k, the determinant of the k by k submatrix is 0. So these are kind of trivially inside of my ideal that I'm really interested in. Sometimes these actually generate the whole ideal. So for example, sometimes when, what's an example of this? Well, n and I are really the same thing if the matroid that I'm looking at is something called a positroid. So what's a positroid? A positroid is a matroid that can be realized by a matrix whose minors are positive, okay? And so this is a result of Knudsen, Lamb, and Spire. And you might say, well, this looks, maybe things are going to be kind of trivial. These polynomials are going to be easy to find. And there's a result from the 80s, that's I think more or less simultaneously due to Nev and Sturmfels, that should give us the intuition that no, this is probably not going to be the case, because these matroid varieties can be pretty complicated. And the measure of complexity that I'm going to use here is sort of, well, it turns out they can have arbitrary rational singularities. So Vx can have any singularity that can be defined over the rationals, singularity. And this is due to Nev and Sturmfels. So knowing, I guess, that these these varieties can have pretty nasty singularities and be kind of wild. Makes you sort of pause and think, well, I don't want to make any assumptions about their ideals. Their ideals might be pretty wild too. So then where are we? We're sort of here. On the one hand, we have the positroids, right? And Knudsen, Lamb, and Spire showed that matroid varieties of positroids are very simple algebraically. And on the other hand, in their paper, Knudsen, Lamb, and Spire warn people that asking questions about matroid varieties can lead you into sort of a terrible abyss, right? Of very difficult questions that are very difficult to answer. And they kind of say, like, you should be careful about going there. So where are we for the rest of the talk? I claim we're somewhere between positroids and the abyss. And where we are is we're going to be working with matroid varieties that have interesting geometry, rich geometry and combinatorics that's going to allow us to derive equations in the matroid variety in ways that we can really understand. Okay, so using the geometry and the combinatorics. All right.
So Jessica, we have a question in the chat.
Sure.
So someone asked, is Ix equal to the square root of Nx?
It is not equal to the radical of Nx. What we show in the paper, it's we think it's equal to the saturation of Nx by the I don't know if it's equal to the saturation. You have to. It's not the radical. It's not. It's not going to be the radical, I think.
I misspoke. Yeah, radical.
Any other questions? Let's see. Okay. Oh yeah, and Tom earlier caught on my typo that it was that 127 was not in there. Okay, so this is where we are. All right. So now I want to introduce the tool that's going to let me describe these bracket polynomials in a way that's sort of going to be understandable by humans, at least humans who love combinatorics. And the tool that I'm going to use is the Grassmann-Cayley algebra. So Grassmann-Cayley algebra. And when I learned about the Grassmann-Cayley algebra, I actually learned about it reading papers in rigidity theory. And I just thought it was the most wonderful thing I'd ever encountered. And it seems like in pure mathematics, people don't use it very much. People in algebraic geometry didn't know about it too much. People in commutative algebra weren't talking about it very much. Sometimes engineers, I think, actually knew about it more because people use it in robotics and things like that. And I've spent the last decade of my life trying to proselytize for the Grassmann-Cayley algebra. So it really does go back to ideas of Grassmann way back when. And he was really, I think, ahead of his time. And the Grassmann-Cayley algebra didn't really resurface in a strong way until, I think, the 70s. And Giancarlo Rota sort of put it on firm footing for us. And I'm going to only define it in a special case because we're going to be working exclusively in the plane, more or less. So I'm going to be thinking about the Grassmann-Cayley algebra, and I'm going to be thinking about it sort of interchangeably as the Grassmann-Cayley algebra on C3 or the projector space P2. So what is this thing? It's the exterior algebra on, in our situation, C3 plus one extra operation. Okay, and so what are the two operations? So the first operation that I want to think about is what we call the join. And the join is just the usual exterior product of vectors, so exterior product. However, we're going to write it a little differently. So, and I've been doing this for 10 years now, so it actually seems normal to me at this point. We're going to write it upside down. Okay, so if I have an X and a Y in C3, usually we'd write X wedge Y for the exterior product, but in the Grossman-Cayley algebra, we write X VY, or often we just write XY, where it's understood that by juxtaposition, that's a join, okay? Why would we do this when everyone is used to writing the exterior product the other way? Well, the exterior product of two vectors is not zero exactly when those two vectors are linearly independent. In other words, they're the basis for a subspace. So I want to think about joins, and exterior products is really like, these are subspaces. They correspond to the bases of subspaces. And if I take the join of two vectors, so now instead of thinking about them as vectors, I want to think about them as points in P2, and that join is going to be the line joining them. So the line joining X and Y, okay? And if I joined three vectors that were linearly independent together, their join would be all of P2 or all of C3, okay? The other operation is the meet, and it's going to correspond to intersection of subspaces. And because intersections we write with a cap, it makes more sense to use the V, or not the V, the wedge to represent meet. So for example, I'm just going to define the meet in a special case because this is all we need for the talk. If I have the join of two vectors x, y, and I want to meet it with the join of two other vectors, w, z, here's what it's defined to be. It's the bracket xwz times the vector y minus the bracket ywz times the vector x. So remember, these brackets are literally determinants. So the bracket is a number. So this is a linear combination of the vectors x and y. Or you can also think of it as a point on the line spanned by x and y in P2. So this is the point in P2. And I can see that it's on the line joining x to y. You can also rewrite this and see it's on the line joining w and z. So when I look at the other left-hand side of my equation, xy is a line, wz is a line, and this thing is a point that lies on both lines. So it's the intersection, should represent the intersection of the two lines. Okay. So now that we know how to do this meeting, let's make a computation. Let's do an example. So let's compute out the following Grossman-Cayley algebra expression. Let's look at 1, 2, meet 3, 4, joined with 5, 6. So what is this? Well, I'm going to do what's in parentheses first. So that would be the bracket 1, 3, 4, 2 minus the bracket 2, 3, 4, 1. And then this is joined still with 5, 6. And then what I get is 1, 3, 4, 2, 5, 6 minus 2, 3, 4, 1, 5, 6. Okay. Have we seen this polynomial before? Yeah, we really have. I can find it. Look. Oh, where'd it go? There it is. 1, 3, 4, 2, 5, 6 minus 2, 3, 4, 1, 5, 6. It was that mysterious polynomial f that had to vanish on any matrix that had the same matroid as that funny 3 by 7 matrix that I started the talk with. So let's see if we can kind of use Grossman-Cayley algebra stuff to understand what's really going on here. So let's look at the, you know what, I'm gonna move this, I wanna move that over, but I can't because I have to I have a picture that I have to use in a minute. Anyway, so this here is a line. That's a line. 1, 2 meet 3, 4 is a point on the line. This is another line. 5, 6 is another line. So if I look at the left-hand side, using geometry, I can interpret when f has to vanish. And when f vanishes, really is, okay, I have 3 lines, 1, 2, 3, 4, and 5, 6. And the polynomial will vanish exactly when those 3 lines are coincident, when they meet at a point. And that's not something you expect to have 3 lines in P2 do, right? You expect 3 lines in P2 to generically kind of be a triangle, okay? Well, let's look at, let me try to draw the points of the matroid corresponding to the 3x7 matrix that I gave in the first place. So we can take a quick look at this thing. You'll notice that the first row is all 1s. And so that's supposed to give you the idea that I'm really thinking of the columns as living in projective 2 space in P2. So I'm going to throw away that first row and draw the points in the last 2 rows, right? Because I'm working in an affine patch of P2. And if I draw them, what I've really got is the following. The point, let me draw my coordinate axes in. So the column 1 corresponds to 1, 0. And column 2 is 2, 0. Column 3 is 0, 1. Column 4 is 0, 2. Column 5 is the point 1, 1. Column 6 is the point 2, 2. And column 7 is the origin. And what I can see is that the columns of the matrix that I started with satisfy this funny condition that if I pair up the columns in these way, they span 3 lines that are coincident. And that's unusual. It's not to be expected. And that's why any matrix with the same matroid has to satisfy this polynomial f. So we first saw this example in a paper that came out of Nick Ford's thesis. And in that paper, it says that actually the ideal of the matroid that you get is exactly on the nose equal to the thing generated by the 3 brackets, 1, 2, 7, 3, 4, 7, 5, 6, 7, and the polynomial f. And I saw this and I was like, wow, why? I want to understand this. Because there wasn't a proof in the paper, it was just stated. And it was always, once you understand where f comes from, then one inclusion is clear, that has to work. The other inclusion is still kind of mysterious to me if you're not doing it just by computation, right? Macaulay 2 or something like that. And anyway, so we said, wow, are there other examples of interesting matroids that we could define where we could try to find non-trivial equations in their ideals? And so that's what I want to talk for the remaining minutes of the talk.
Sorry, Jessica, quick question.
Sure.
We have a request to see the original matrix again.
Sure thing. So here's the matrix. So you can see the first 2 columns are 1, 0, 2, 0, sort of 0, 1, 0, 2, 1, 1, 2, 2, and 0, 0.
Great, thank you.
You're welcome. So now I'm asking, are there other interesting matroid varieties with equations that we can derive via geometry and combinatorics in a similar way? Okay, so the answer is yes. And we found sort of 3 infinite classes, families of Matroid varieties, where we could get some nice equations that we could explain why they're there. And the prototype for all of these had to do with Pascal's, was understanding what happens with Pascal's theorem. So actually, if you think about your favorite theorems in projective geometry, the example I just showed you is really secretly Desargues' theorem. So you can sort of think about that if you want to later. But now I want to think about Pascal's theorem. So Pascal's theorem. So here, this is something I didn't want to draw. So I have it pre-drawn for us. So Pascal's theorem is about when 6 points lie on a conic. So it says that if I have points 1, 2, 3, 4, 5, 6 points in P2, these points lie on a conic if and only if the following things happen. Okay, so here I have, in the picture on the right, I have my 6 points. And the crazy lines that I've drawn, it's really just a hexagon. So that's why they're numbered in that funny way, because if you start at 1 and you go to 2, you go like 1, 2, 3, 4, 5, 6, back to 1. So you can see I closed it up. It's just a hexagon, okay? And if you draw that hexagon, and then you look at these, and you look at the intersection points that are labeled 7, 8, and 9, then those the 6 points are on a conic if and only if 7, 8, and 9 are collinear, okay? But now that we know the Grassmann-Cayley algebra, we can rewrite Pascal's theorem in the following way. It's really that if I look at 1, 2, meet 4, 5, so that's the point 7, okay? And if I look at the point 8, which is 2, 3, meet 5, 6, so that's the point 8. And then point 9 is really 3, 4, meet 1, 6, okay? So Pascal's theorem is really saying that this Grassmann-Cayley algebra expression is equal to 0 if and only if my 6 points lie on a conic, okay? Or if, yeah. All right, so the Pascal's theorem was really one direction, and the other direction is really due to Breckenridge, and Maclaurin, okay? And so I claim that using Pascal's theorem, we can get an interesting matroid. Okay, so what we're gonna do is let AX be a 3×9 matrix, 3×9 matrix, whose columns are the 9 points from Pascal's theorem. Okay, so whose columns are 9 points that satisfy Pascal's theorem. Okay, so there are 6 points lying on a conic, and then the 3 points, 7, 8, and 9 that are the collinear coincidence conclusion of Pascal's theorem. Okay, so this matrix is going to have 7 non-bases. So it has 7 non-bases, and I'll write some of them out that correspond to non-vanishing brackets. So for example, one of them comes from the fact that the points 1, let me see, where's 2? 1, 2, and 7 are collinear, so that bracket has to vanish. Also that 4, 5, and 7, right? So there are 7 of those, and each of these is in the ideal NX, which is contained in IX. But we can use the conclusion or the reinterpretation of Pascal's theorem in terms of the Grassmann-Cayley algebra to get more equations. So if I have 1, 2 meet 4, 5, joined with 2, 3 meet 5, 6, joined with 3, 4 meet 1, 6, I can expand this out. So what does this look like? It looks like 1, 4, 5, 2 minus 2, 4, 5, 1, joined with 2, 5, 6, 3 minus 3, 5, 6, 2, joined with 3, 1, 6, 4, minus 4, 1, 6, 3. And if you keep going, what you will get is a degree 4 bracket polynomial. So it will, I'm going to write it out in its full glory for you, I think. So it's 1, 4, 5, 2, 5, 6, 3, 1, 6, 2, 3, 4. That's its first term. Minus 1, 4, 5, 3, 5, 6, 4, 1, 6, 2, 1, 3. That's the second term. There's only one more term left, so don't worry. And then 2, 4, 5, 2, 5, 6, 3, 1, 6, 1, 3, 4. Phew. So if I just wrote that out to you, you would say, I don't know where that came from. And it's a degree 4 bracket polynomial. So degree 4 in brackets or Plücker coordinates. It would look way worse if I had just written it out with all of its variables. So really, I'm suppressing the notion, the fact that this is a degree 12 polynomial in the entries of some 3×9 matrix. Okay. So here I have one extra polynomial that would be a little mysterious if I hadn't derived it using the Grassmann-Cayley algebra, but that now I can, we know where it comes from. It came from Pascal's theorem. We can get more polynomials in the same way. So there's more juice to be squeezed from Pascal's theorem. There are degree 3 and 2 polynomials as well. Okay, so one thing that you might notice about this big long polynomial is that it only involves the points 1 through 6, all right? But here's what I'm going to do. I'm going to replace the first meet by the point 7, because 1, 2 meet 4, 5 actually corresponds to the point 7. So I can replace it and I get 7 joined with 2, 3 meet 5, 6, joined with 3, 4 meet 1, 6. I'm not going to do that all out for you, but I claim this is a degree 3 polynomial. And I could do that with any of the 3 points. I could put an 8, I could replace the middle meet by an 8 or the last meet by a 9, or I could do it 2 at a time, right? So if I did 7 and 8 and met that with 3, 4 meet 1, 6, that is a degree 2 polynomial. Whoa! And so what we do in the paper is we show that these polynomials are not in the ideal NX and that they're independent, okay? And then I just want to end by saying, how do we generalize this? So we had 3 ways of generalizing this. Generalize. 3 generalizations. One was to just put more points on a conic in P2. Okay, so if you put more points on a conic, you get more weird matroids that sort of, there are lots of points on a conic. That's a unusual thing. It's not generic. And so that you get these interesting matroids. And we can find lots of equations, non-trivial equations in the matroid varieties. You can put points on higher degree curves. So higher degree curves in P2. And here, one way of thinking about Pascal is to sort of think about Pascal's theorem as a special case of a Cayley-Bacharach type theorem. And so using Cayley-Bacharach, we're able to construct an infinite family of matroids where we can find some equations in the matroid varieties that aren't trivial. And then the last thing we did, which is my favorite thing, is we generalized this to higher dimension. So instead of points in P2, we look at points on what are called rational normal curves in PD. So where would you get this idea? So a rational normal curve is just an embedding of P1 into PD. And actually, a conic is a rational normal curve embedding P1 into P2, okay? So you can re-envision Pascal's theorem as saying, when does 6 points lie on a rational normal curve in the plane? And 6 is 2 plus 4. So the correct generalization to higher dimension is to ask, when did D plus 4 points lie on a rational normal curve of degree D? And there's a beautiful paper from last spring by Caminata and Schaffler that I highly recommend reading. So this is from 2019, where they were able to give a nice Grossman-Cayley characterization of when D plus 4 points in P to the D lie on a rational normal curve using the Grossman-Cayley algebra in a way that generalizes Pascal's theorem in just a really beautiful way. And using their result, we can take the Grossman-Cayley expressions that they've got and cook up equations that have to be in the matroid variety. Okay, so that I think I'm out of time, and that's where I want to stop. Thank you very much.
All right, great, thank you. Let's give Jessica a quick virtual round of applause. If you want to ask questions, just go ahead and queue up in the window, or you can unmute yourself. I'm going to go ahead and use this opportunity to. I was reading Darrage Grinberg's questions, and one thing he commented on was this person commented on was the first time seeing Pascal's theorem drawn inside the ellipse. So my question actually is. There are, I think, 2 other versions of Pascal's theorem where you can like draw intersections outside. Is that also expressing the same fact?
Yeah. There are different ways, and you can arrange the hexagon so it actually looks like a hexagon, or you can. Yeah.
Right. Okay, cool. All right, so Yibu Gao has a question, and what is the relation between the polynomials that you have and Plucker relations or Plucker relations?
That's a good question. Right. So the polynomials that we have are not equivalent to each other by Plucker relations. They're really distinct and different. If that's what you're asking.
Yeah, I confer. All right. Yeah, and then. Someone remind me that yes, the geometry doesn't matter or where it's drawn.
Yeah, it's the combinatorics that matters, I think.
Yeah, exactly.
I was wondering if like there's like if it would make sense at all to try and tropicalize this or think of it from a tropical perspective, like.
So I am not a tropical person, though I know there's like one of my #1 things to learn about is tropical geometry. If you want some interesting connections to tropical geometry, I'm just trying to think. It's a good question and not one I've thought about because it's like outside my wheelhouse. I was going to say, there might be some connections to, but that I'm thinking of rigidity theory stuff. So yeah, it's not something we thought about because we haven't been thinking tropically, but.
Yeah, it was just, and I don't think this is tropical geometry because at first it made me think, because I more of see talks in the area, not that I do it, but it reminded me at first of Bergman fans, but then when I looked them up, those are actually including like circuits of matroids, not, but anyway, I was just curious. It's very interesting.
Thank you.
So I have a question. If you look at maybe two-step flags, is there like a Grassmann-Cayley algebra also in that situation? Or?
Oh, for different kinds of, yeah, I don't know. I mean, right, so for flag varieties, what kind of algebra do you get on flag varieties? I don't know. That's an interesting question, though.
So I would like to maybe not really answer this by saying there is a paper by Crepo called An Algebra of Pieces of Space, and he at least mentions flags as something you can compute with, but I've never read that actually.
Thank you.
I have a question. Wondering, does this, how this bears on the more general question? So you're given an arbitrary arrangement of points, then to find the equations that characterize the matroid on those points.
Yeah, so I don't know, I thought about this a lot, about like, what can you say really generally? And the thing is, so I got my start in math thinking about ideals of linear subspace arrangements, right? And I think there was a sense there that, well, these are linear subspaces. If you take a variety that's a union of linear subspaces, you should be able to say something nice about its ideal because the varieties are, after all, unions of subspaces. But I came around after years of thinking of it to believe that actually you can only really get something nice combinatorial statements when those subspaces have interesting and rich combinatorics. Okay, and I suspect that matroid varieties are sort of similar in that if the points that are the ground set of your matroid are just sort of random and arbitrary, then you're kind of in this Nev-Sturmfels world where like anything can happen, kind of. Oh. And I don't really know if there's a reason to believe, if the points aren't interesting combinatorially, that the equations will have any combinatorial or nice sense either. But if the combinatorics is rich and unexpected, and there are lots of things lining up, right? Lots of triples of collinear points that you'd never expect. That's when you can say something interesting, I suspect.
Well, I'm wondering, that's a given the arrangement of points, there'll be some. There'll be if it's not in general position, there'll be some dependencies.
That's right.
And so you kind of read out from the okay. Kind of read out from the basically read out from the matroids of the equations.
I mean, you can certainly read out the, if you're talking about points in P2, you can certainly read out all the generators of that ideal I called NX that are just like the vanishing brackets.
Okay, yeah.
But the more mysterious ones, the ones that aren't just monomials, it's not so clear to me how you get them.
Oh, I see. Okay.
Yeah.
So what you've investigated some special matroids that arise from algebraic structure.
Yeah. And so these theorems, it's like, take your favorite theorem in projective geometry.
Oh, okay.
Like Pappus's theorem is a special case of Pascal's theorem, and you can get something nice there, and
So it's a matroid characterization of of classical-like theorems in geometry.
Yeah, that's right.
Or rather, a Matroid characterization of the point line arrangements that express theorems of geometry.
Yeah, yeah, and that's why we sort of looked also at Cayley-Baccarat type stuff, right? These are sort of points, unusual things to know about points and equations that vanish on them, and that's where we could hope to get results.
Okay.